Hello friends, we are going to continue our discussion on block electrons. In the previous lecture, we converted time-independent Schrödinger equation to a system of linear equations. In this lecture, I am going to solve the system of linear equations to get the energy eigenvalues and show that energy values are not continuous but gapped in case of block electrons. This is the form of time-independent Schrödinger equation we are familiar with. When U of x is a periodic potential, time-independent Schrödinger equation is converted to a system of linear equations shown in the form of a matrix here. Note that each row of the matrix can be expressed as lambda k minus epsilon times ck plus sum over g ug c k minus g is equals to 0, where lambda k is equals to h cross square k square divided by 2m, which is equal to the energy of a free electron with wave vector k. Let us verify the third row of the matrix. We have lambda k minus epsilon times ck plus u times c k minus b plus u times c k plus b. Note that size of the matrix depends on how many terms enter the sum over g. For example, for a given k, say sum over g has 2 terms. That is, if this is the k point we are talking about, then we have to consider 2 terms, k2 minus b and k2 plus b. In that case, there are 3 non-zero entries per row. If sum over g has 4 terms, that is, if we take k2, then we have to also consider k2 minus b, k2 minus 2b, k2 plus b, and somewhere there will be another point, k2 plus 2b. In that case, there are 5 non-zero entries per row. So we have a system of linear equations representing time-independent Schrödinger equation for independent electrons in a lattice. Note that these are not free electrons because we have non-zero potential U, which has the periodicity of the lattice. Assume that potential U vanishes. In that case, we should get back the free electron results. Let us verify that. Clearly, when U vanishes, all ck minus g is equals to 0 except for ck, and E is equals to h cross square k square divided by 2m. Thus, energy eigenvalue is same as the free electron value when U vanishes. Let us also check whether block states are converted to free electron eigenfunctions when U vanishes. We know that the block state psi k of x is e power ikx times uk of x, where uk of x is given by this sum. If all ck minus g is equals to 0 except ck, the function uk of x is a constant. Note that any constant function also has the periodicity of the lattice, so that Bloch's theorem is still valid from mathematical point of view. But this is only a mathematical argument, as we really do not mean a constant potential when we talk about the periodic potential in a solid. Since uk of x is a constant when potential vanishes, psi k of x is e power ikx, which is same as the eigenfunctions of free electrons. Whatever we deduced for block electrons will coincide with free electron results if we make potential U to be equal to 0. Thus, we can say that free electron is a special case of block electron. When we discussed basics of quantum mechanics, we have seen that if there is a potential barrier, part of the incident wave function is reflected and part of it is transmitted, depending on the barrier height and barrier width. Now, we are dealing with barriers which are repeated periodically in space. Can you estimate the amount reflected due to the periodic potential? For this purpose, let us design a simplest possible model. We just take two Fourier components of psi of x. That means we make ck minus 2b equal to 0, ck plus b equal to 0, and ck plus 2b equal to 0. And we have only two non-zero c's, ck minus b and ck. Let us understand what is the purpose of doing so. Note that if we select some k point greater than 0 and lying in the first preloading zone, for example, this point. In that case, k minus b is less than 0. Thus, e power ikx is the incident wave traveling from the left to right in the lattice. Since k minus b is less than 0, e power I k minus bx is the reflected wave traveling from left to the right in the lattice. If we calculate the ratio of the coefficients ck minus b divided by ck, that will tell us how much is reflected due to the periodic potential. Thus, the wave function is psi k of x is equals to ck e power ikx plus ck minus b e power I k minus b x. Note that we have taken k to be positive and lying in the first preloading zone. That means ck times e power ikx is a wave traveling from the left to the right of the lattice. On the other hand, k minus b is less than 0. Thus, the reflected wave e power I k minus b x is traveling from the right to the left of the lattice. We are looking to solve for ck at ck minus b. Let us multiply the matrix with the column vector. So, if we multiply this row with the column vector, then the first term is 0 because ck minus 2b is equals to 0. Then we have a non-zero term, that is lambda k minus b minus epsilon times ck minus b, plus we have u times ck. This is equal to 0. Then we multiply this row with the column vector. So the first term is 0. The second term is u times ck minus b plus lambda k minus epsilon times ck is equals to 0. Thus, we get two equations and we have two unknowns to solve. It is very easy to solve two unknowns from two equations. We know that for non-trivial solution to exist, the determinant must be equal to 0. So let us expand the determinant and find the solution. So lambda k minus epsilon times lambda k minus b minus epsilon minus u square is equals to 0. which can be written as epsilon square minus lambda k minus b plus lambda k times epsilon plus lambda k minus b minus u square is equals to 0, which implies that epsilon is equals to lambda k plus lambda k minus b divided by 2 plus minus half square root of lambda k minus b minus lambda k whole square plus 4 square. In case of free electrons, we have only one value, E of k is equals to h cross square k square by 2m for a given k. In case of block electrons, for a given k value, we have two energy values, one for plus and another for minus. Using a code, let us plot the energy values of block electrons as a function of k. We are going to plot energy values for k ranging from 0 to 2 pi by a. Note that we take a is equals to 1. The range of k values is defined here in the code. The g point is taken to be 2 pi by a, which is defined here in the code. We set h cross square by 2m is equals to 1 such that lambda k is equals to k square and lambda k minus b is equals to k minus b whole square. Lambda values are calculated using a user-defined function here in the code. Using a for loop, we calculate the energy value for the first band and for the second band. For a given value of k, the first band has lower energy and the second band has higher energy. Then we plot the first and second band and compare with the free electron values. This is the code for plotting the first and second band as a function of k ranging between 0 and 2 pi. We define k and b here. We define the value of u here. The two bands are calculated at different k points using the for loop. We plot the bands and compare with free electron values here. Let us run the code for different values of u. We start with u equal to 2. The blue line is for free electrons, green and orange line is for the first and second band respectively. The vertical red dotted line shows the first Brillouin zone boundary lying in the middle of the two reciprocal lattice points. The gap between the first band shown in green and the second band shown in red is minimum at the Brillouin zone boundary, that is at the red dotted line. Now let us run it for u equal to 1. This is how the plot looks like for u equal to 1. And now finally let us run it for u equal to 0. This is how the plot looks for u equal to 0. We compare three cases, u equal to 2, u equal to 1 and u equal to 0. Clearly for u equal to 0, block and free electron energies coincide everywhere as expected. At u not equal to 0, block and free electron energies differ from each other mainly near the first Brillouin zone boundary shown by the red dotted line. That is, they differ mainly in this region. Otherwise, as we move closer to k equal to 0 point, that is here, they coincide. Thus, away from the Brillouin zone boundary, free electron picture holds good. Note that band gap is defined as the energy gap between the first and second band at the Brillouin zone boundary. That is, this is the band gap. The value of band gap increases with increasing U. With a very small modification of the previous code, we can plot band gap as a function of U. We vary U from 0 to 2 using a for loop. Band gap is the energy difference between the maximum of the first band and the minimum of the second band. This is the code for plotting band gap as a function of U. Band gap is calculated by varying U between 0 and 2 using a for loop. We calculate the maximum of the first band and minimum of the second band and calculate their difference here. The difference between the maximum of the first band and the minimum of the second band gives the value of band gap. Let us run the code. From the plot of band gap as a function of U, clearly band gap increases linearly with the magnitude of U. Note that increasing the value of U from 0 to 2 increases the band gap from 0 to 4. Thus, we can say that e.g. the band gap is equals to 2 times U. In case of block electrons, for a given K, there are 2 energy eigenvalues as shown here. This is unlike free electrons where we get only one value, E of K is equals to h cross square K square divided by 2m for a given value of K. Using a code, we have found that epsilon of free and block electrons differ from each other mainly near the Brillouin zone boundary. Let us see whether we can analytically verify this or not. We redefine K in terms of its distance from the first Brillouin zone boundary shown by the green line. We write K is equals to B by 2. So this green line is located at B by 2 and delta K is the distance from the Brillouin zone boundary. And we write K as B by 2 minus delta K. And then we rewrite lambda using this relation. So lambda K will be equal to lambda B by 2 minus delta K because that is how we define K now. And this is equal to h cross square by 2m B by 2 minus delta K whole square. Similarly, K minus B will be equal to B by 2 minus delta K minus B, which is equal to minus B by 2 minus delta K. Thus, lambda K minus B will be equal to lambda minus B by 2 minus delta K, and which is equal to h cross square by 2m B by 2 plus delta K whole square. Let us substitute these values in the equation of energy for block electrons. We have redefined K in terms of its distance from the first Brillouin zone boundary given by delta K. Now we have to rewrite lambda K and lambda K minus B in terms of delta K and substitute in this equation. Let us do that. So we have lambda K minus B plus lambda K divided by 2 is equals to half h cross square by 2m, and we have b square by 4 plus e delta K plus delta K square plus b square by 4 minus b delta k plus delta k square. These two terms cancel out, and this is equal to h plus square by 2m b square by 4 plus delta k square. Similarly, lambda k minus b minus lambda k divided by 2 is equals to half h plus square by 2m b square by 4 plus b delta k plus delta k square minus b square by 4 plus b delta k minus delta k square, which is equal to h plus square by 2m b delta k. Let me quickly summarize what we have done so far. We have redefined k in terms of its distance delta k from the first Brillouin zone boundary located at pi by a. So this is how we write k in terms of b by 2, the first Brillouin zone boundary, and delta k, the distance of k from the first Brillouin zone boundary. Then we rewrite the lambdas in terms of delta k. Then we substitute in this equation the values of lambda, and if we do that, then we can rewrite the energy eigenvalues in terms of delta k. This is how the energy eigenvalues of block electrons look like if we express it in terms of delta k, where delta k is the distance of the k point from the first Brillouin zone boundary. Assume delta k to be very small, that is, it is very close to the first Brillouin zone boundary. Why we are doing this? Because we found from our numerical code that energy values between block and free electrons differ mainly in a region close to the first Brillouin zone boundary, and we want to check it analytically. In case of very small k, we can write this term, that is 1 plus h cross square by 2m whole square p square delta k square divided by u square whole power half. So when delta k is very small, we can write it approximately as 1 plus half h cross square by 2m p square delta k square divided by u square. Now note that the first term h cross square by 2m times b by 2 whole square is equals to lambda b by 2, that is the energy of free electron with wave vector b by 2. Thus, we can write energy is equals to, so the first term is lambda b by 2. The second term is plus h cross square delta k square divided by 2m. The third term is plus minus u times 1, and then we have plus minus, so we use the small k approximation, and then this turns out to be h cross square by 2m delta k square times h cross square by 2m b square by 2 times, so 1 u gets cancelled, so this is 1 by u. Note that this term is 2 times lambda b by 2. Thus we can rewrite the energy in terms of delta k, when remember that delta k is very small, that is k is located very close to the first Brillouin zone boundary. So in that case energy is lambda b by 2 plus minus u, so these two terms, plus h cross square delta k square by 2m. So that means we take this term and this term, and then this is like 1 plus minus 2 lambda b by 2 divided by u. Thus we have found the approximate form of energy eigenvalues when k is very close to the first Brillouin zone boundary. That means this equation will hold good in case of this blue point, because this is closer to the first Brillouin zone boundary, but it will not hold good for the magenta point, which is far away from the Brillouin zone boundary. Now let us put delta k is equals to 0. In that case the second term will vanish completely, and the energy eigenvalues exactly at the zone boundary is equal to lambda b by 2 plus minus u. We know that the energy gap at the zone boundary between the first band and second band is defined as the band gap, and from this expression we find that the band gap is equal to 2u. Thus if we compare with our code, then it matches exactly what we have found in our code. Similarly, from our analytical result, we find that energy varies as delta k square near the Brillouin zone boundary. You compare with our code, and then we see that indeed the energy eigenvalues vary as k square near the Brillouin zone boundary. Thus, whatever we have observed with our numerical code is matching very well with the analytical expression.